Welcome back. In this video, we're going to talk about the dot product formula for the directional derivative, which is an alternative to taking limits. Remember that when we defined a directional derivative, we started with an explicit representation of a differentiable function, f of x comma y. This differentiable function, we started with a point in the domain of this function called a comma b. And then we also defined a unit vector u, which was going to be used as the direction for our directional derivative. To construct the directional derivative, we created a single variable function, which we'll call in this video z of t. And z of t came from evaluating the output of our function f along a line through the point ab in the direction of u. Notice that since f was a two-variable function, we indeed needed an input that was two variables. And we said that L of t, in this case, we're calling the parameter t, was given by x of t, y of t. And each of these were points along a parameterized line passing through the point AB in the direction of u1 comma u2. So this would be b plus tu2. Recall that L of t was a line in the domain space of f given by the equation p naught, which is a point, plus t times the direction u, which of course was a comma b, plus t times u1, u2. And again, u1, u2 represents a vector, a direction vector of length 1. The output of the single variable function z of t is the z value of points along the surface that result from evaluating our function f of xy along the line L of t in the domain. Moreover, the derivative z prime of t, which is the single variable derivative or ordinary derivative of the function z of t with respect to the parameter t, represents the slope of the tangent line at an input point x of t comma y of t along the line L of t. With this in mind, we can write the directional derivative of f with respect to the direction u at AB. That's what this notation said. We said in the last video this directional derivative came from taking a limit with respect to h, where we measured the rise over the run as the change in input points along our line. So this was a plus hu1, b plus hu2, and of course we subtracted a comma b. But if you recognize this, we could have equally said that this was the limit as t goes to 0, where this is now t, and this would be f of a plus tu1. So we're just changing the parameter name here, and you'll see why we did this in a second. Remember, the reason that we use the parameter h in that original definition was that we like our limits of secant lines to have parameter h. But in this case, when we have t going to 0, we can now think about this as a derivative of the single variable function z with respect to a parameter t, and we're going to do this at t equals 0. So this is now what we call z prime at 0. Because notice that if you put in 0, you would have a comma b. L of 0 equals the point a comma b. And then we're just going to let our limit go along u towards that point. Okay, well, we have seen something quite special here. When we look at z prime of 0, this of course is the ordinary derivative of z of t evaluated at t equals 0. which is going to be called the ordinary derivative of f of L of t evaluated at t equals 0, which of course, because L of t is a parameterized vector valued function with two outputs, we would call this x of t comma y of t. And of course, we're going to evaluate this derivative at t equals 0. But this is the multivariable chain rule that we just saw in lesson 10. So here we call this the multivariable chain rule. There it is. And again, remember in the multivariable chain rule that we use this chain rule tree. At the top of this tree, we have the function f. And then we have our intermediate variables, what we call x and y, and then we have our one independent variable that was called t. And notice that we have two branches along this particular chain rule tree. We have the branch consisting of the partial derivative of f with respect to x, and then we have an ordinary derivative of x with respect to t, since x only has one input variable. Same thing's true on the other side, except in this case we have the partial derivative of f with respect to y, and then we have the ordinary derivative of y with respect to t. The chain rule said that when we want to take this particular derivative, we would multiply the derivatives on the branches. So here this would be partial derivative of f with respect to x multiplied by the ordinary derivative of x with respect to t. And then we would add the products of those branches. So this would be the partial derivative of f with respect to y times the ordinary derivative of y with respect to t. And this entire chain rule was going to be evaluated at t equals 0. We can do something further because x of t was given by a plus tu1. That implies that the derivative of x of t, perhaps we call it x prime of t, is just going to be u1. And then the same thing's true for y of t, since the function y of t is a linear function in terms of u2, where it's b plus tu2. That implies y prime of t is just u2. Okay. Well, this gives us kind of a powerful thing here. This was going to be our derivative evaluated at t equals 0, but at t equals 0, the x of t coordinate is going to be a comma b. And then here, the derivative of x with respect to t at t equals 0, well, we just saw that that was going to be u1. Similarly, the partial derivative of f with respect to y evaluated at t0 would be the partial derivative of f with respect to y at the point AB. And then the derivative of y with respect to t ordinary would be u2. And the way to think about this is just look up here. We'll do one quick confirmation. If I try to evaluate x at 0, indeed I get a. Y at 0 equals b, which means the partial derivative of f with respect to x at t equals 0, that's going to be the partial derivative of f with respect to x at the point a comma b, which is what we have right here. Okay. And this, I don't know if you recognize it, but do you see a dot product there? Yeah, you got it. The first component of this dot product is going to be the partial derivative of f with respect to x evaluated at ab. The second component of this first vector would be the partial derivative of f with respect to y evaluated at ab. And then the second one, the second vector is just going to be u1, u2. This is now a functional derivative mechanism to take the derivatives that does not require limits. This vector right here, we're going to define this to be the gradient vector of f at a comma b, which is just quite amazing. We talked about this earlier in life. And then the second vector is going to be the vector u. So the gradient vector is the vector, each component of which is the partial derivative, and then this is going to be a function of two variables. Here the variables take constant values a comma v. This allows us to compute the directional derivative without a limit. Generally, when taking derivatives with a limit, I like to think about plucking my eyebrows out with tweezers as more fun than taking limits to find derivatives. What's nice about this is I don't have to go bald in terms of my eyebrows, my beautiful, beautiful eyebrows. Instead, I can just take this dot product. This thing can be evaluated quite quickly. So the gradient of this can be found by just taking partial derivatives. And then if I have a unit vector in the direction that I want to go, I can just take that dot product. So this is an alternative method to finding the directional derivative in the direction of u that does not require limits and is based on this chain rule. Please study this derivation because many, many deep theorems are going to come from this. In the next video, we'll take a look at some examples of how to use this. See you there.